welcome everybody. My name is Paul Purcell, and I'm a developer relations engineer at Unity. This talk is going to be about debugging Unity source. So at the end of the talk, I'm hoping that you guys are feeling a little bit more comfortable about the hows of how to debug Unity, but also that you have a more advanced toolkit to actually be successful at that. Before we get started, I just want to say a little bit about myself. So as I mentioned, I'm a dev relations engineer, and what that means is my primary responsibility at Unity is to provide engineering support to customers like yourselves, support customers, as well as source code customers. I've been at Unity for just over 2.5 years, and also part of what I do is go on site to your office, and I provide project reviews, which are essentially multi-day sit-downs where we profile your project and we try to find issues and we try to pull out some best practices and find solutions to make your game run better. I'm based in San Francisco. I've got my email up there if you guys need to contact me. So before we get started, I just wanted to give a quick overview of kind of what we're going to cover today. So to start out, I'm going to just give kind of an overview of debugging Unity source code builds. So as you saw in the previous presentation, we now have the capability to actually debug the dependency graph tree. So I'm going to cover kind of how to do that. And then after that, I'm going to cover actually debugging the Unity editor and players. I'll go over very briefly on the how to do that. That's essentially in our documentation, so I won't waste too much of your time there. But then after that, what I want to do is cover some different tips and stuff that you might not find in our documentation that can actually be useful to actually successfully debugging source code. And then after that, I want to talk about some specific tools in our code base. You actually caught some hints of that in the last talk, stuff like diagnostic switches, leak detection, and debug allocators. These are kind of different tools in the code base that you can use to maybe help debug some issues. And then lastly, I'm going to cover debugging runtime tests really briefly. It's not very difficult, but if you don't know what to do, it can be hard to understand. And then we'll have some time left over to Q&A, although it seems like you guys are not the asking questions type, so we'll see if you guys have any questions. OK, so let's get started. Right off the bat, debugging Unity source code builds. So as you saw in the last talk, Unity is partially built with Jam Sharp. As he mentioned in the last talk, it's primarily built with Jam as kind of the core base of building Unity. Jam Sharp is the Jam Plus extension that allows us to write managed C# code to build Unity. Jam Sharp, in terms of source code that you guys have access to, the first official release that you'll find Jam Sharp stuff in is 2017.1. Although, as you mentioned, there are other stuff. There's work that went into it over time in different releases. But this allows us to use C# debuggers like JetBrains Writer, and so that's nice. So a couple of limitations. The only thing that you can actually debug in terms of the build system is just the dependency graph creation. So as of right now, because the majority of the build is actually still done in Jam, you can't debug that part in the same way. So what I'm going to be talking about is just the dependency graph generation, or essentially the files that are written in .jam, .cs files. So just the managed code part. We are still working on potential options for replacing Jam long term, but I don't think we have any solid replacements yet, so we'll keep you posted. OK, so how do you actually do it? So the first thing you need to do is download and install JetBrains Writer. This is the managed debugger that we've built this tool for. It's actually right now the only debugger you can use to do this, so you need to install it. And then, as you saw, I think in the last presentation, you showed off these different command line options. And the -s debug equals 1 is the one that you are looking for if you want to debug the build system. You're going to need to use the Jam entry point, as you mentioned. So ./jam instead of the Perl build script, which is kind of the more generic entry point. And then, of course, editor. The editor command there is to build the editor, and then Mac editor is for Mac editor, and then the sdebug switch is to start the debug. Once you do that, once you run that command, you should get some on-screen instructions on how to proceed. Those look something like this. So if you'll see at the top there, you'll see .jam, editor, sdebug equals 1. I've also included the output the dependency graph option. And then on the bottom 7 lines there, you'll see the next 7 steps you need to take to get the debugger attached. Those steps are essentially just some quick configuration, enable a port, open JetBrains writer, blah, 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 set a breakpoint, attach. It's pretty simple. Once you follow those steps, the build system will automatically determine that you've attached the debugger, and it will automatically continue. So you don't have to do anything else. It'll know that you've attached the debugger, it'll continue the build, and then, miraculously, we hit a breakpoint, and you're on your way. So now you've got JetBrains writer attached, and you've got a breakpoint set, and you can debug. So nice and easy. So the next thing up is visualizing the dependency graph. So there's going to be a little bit of overlap here with what you've already seen, but I'll go a little more detail. Again, it's use the jam generated command line option, so s output dependency graph, and then it'll generate, when it's done, so if you just run that command, it will generate the HTML file that you're looking for at that location, and then you can just open that up in any browser. It's supported on all browsers. And as you saw before, it looks something like this. So it's, you have a HTML browser document that you can view. On the left-hand side, you've got the dependency graph, and then you can drill down into any of those trees. And then on the right-hand side, for any selected item, you'll get some informational context on the right-hand side. And then at the top, there's a search bar, so you can actually search for things that you're looking for. When you drill down into one of the dependency trees, it looks something like this. So, at the top, we have runtime export application.bindings, and then you can kind of drill down and see all of the references and dependencies down into the tree. I kept this short because, as Scott mentioned earlier, it's a mess. So you're really if you're going to be using this, you need to have a mission ahead of time of what you're looking for and what you're trying to get out of it, because you're not going to get very much use by just crawling through this. Just a kind of side note on all of this is that there's more kind of new cool stuff in our documentation. So there's been a fair amount of work going into updating and making our source documentation better. So if you haven't looked at it recently, as of the 2017.1 release, I highly recommend you pull it and actually open that PDF and check it out, because there are new topics, there are updates to old topics, specifically in this area. All of what I've just shown you is more or less documented in the building via jam section. And there's also stuff like how to optimize build times and investigate rebuild causes and other cool topics there. So highly recommend checking it out. OK, so let's move on to debugging Unity editors and players. So debugging Unity is really easy. As you can see, this is a screenshot of our documentation here. It's essentially 4 bullet points. You build Unity, you open up a solution, you go debug, start debugging Visual Studio. You're done. There you go. You're debugging. Actually, debugging Unity can be hard. It's really easy to start debugging in an editor. It can be hard to actually figure out what the problem is or why there is a problem. So most of the talk is going to be focusing on the hard parts. But let's get the easy out of the way. So what do you do to actually debug, get a debugged version of Unity? So the first thing you need to do is you need to make sure that you've built Unity with a codegen equals debug flag, or that you've set codegen to debug in the Perl script. So you might recognize this bottom screenshot here, which is our Perl build PL main entry point, and that's the bottom of the output. And so you can just hit C to flip the code gen to debug, or if you're passing, if you want to pass the command line option, you just use code gen debug. But anyway, you need to have a debug build to get a debuggable version of Unity. Once you build, again, it's really simple. You open the solution. You can find that solution in the source root/projects. If you're on Windows, you'll have to go into Visual Studio folder to find the Visual Studio solution. If you're on Mac OS X, you'll have to go into the Xcode folder. You essentially then just need to open up the right solution. So we have multiple solutions depending on what you're trying to debug. So for instance, there's a Mac editor, and then on Windows, there's a Windows editor, and then there's also like standalone and different solutions for different targets. But for the editor, you're just looking for Mac editor or the Windows editor. And then, of course, you open it up, you hit F5, you're debugging. Of course, you can alternatively just attach the debugger to a running Unity process, as long as that process is a source build with debug code. So pretty easy. Same on the player. The player is a little bit more difficult. So the thing about player debugging is that it's going to be very specific to the platform that you're actually attempting to debug. So the only recommendation here without adding slides for every single platform is you need to actually just go read what we have documented for that particular platform, because every platform is going to have a slightly different set of criteria on what you need to do to properly debug it. You're going to have different IDEs. You need to be using Visual Studio or Xcode or Android Studio or whatever you need for that particular platform. But to boil it down to 4 simple kind of generic points, it's essentially what I said before. You got to build Unity with source for debug, and then you need to build the player with that source editor, and make sure you build a development build of the player. And then you need to follow whatever platform-specific steps come in between there. So sometimes that means you have to open up Android Studio. For iOS, that means you have to drop in the DLL into the player Xcode project. It's just going to depend on the platform. So follow whatever those steps are, and then again, run and attach. What do you know? There you go, you're debugging. OK, so that's the easy part about debugging Unity. We're done with that. Let's get into the hard parts. So the first kind of hard thing about debugging Unity can be debugging managed code and native code at the same time. So typically you have a solution for the native runtime of an editor, or there's the native runtime and or the editor. But then you also have managed code. You have managed code that Unity has written, or you have your managed code that you've written in the player, and maybe you want to debug them at the same time. So let's get into that. So on Windows, Windows is probably the easiest platform to do this on. So with Windows, all you need to do is you need to have 2 different Visual Studio instances. You need one that has the native solution that you're attempting to debug, and one with the managed solution that you're attempting to debug open. And then you can attach both to the same, say, the player. And that's pretty much it. There's only one caveat there, which is that you're going to need to disable some handled exceptions for the native debugger. Because on Windows, you're going to get first chance exceptions sent by the executable to both debuggers. And so, for instance, the native debugger will catch on managed exceptions. And so, that's not very good, because the managed runtime sends a lot of first chance exceptions that are potentially handled. And so you want to be able to ignore those. So the way you can do that is in the native solution. So for instance, you can use Visual Studio 2015. You just go to Debug, Windows, Exception Settings, and then you just uncheck the access violation for that hex code there. That will ensure that the native solution doesn't catch those first chance exceptions, and then you can kind of simultaneously debug. And yeah, that's about it. I mean, after that, you basically have two Visual Studio instances. You can set breakpoints in either. Make sure, go back and forth. It's pretty simple. On OS X, it's a bit harder. So As of today, debugging native code and managed code at the same time, it's not impossible, it's a bit of a struggle. And that is because on OS X, Xcode, which uses the LDB debugger, uses the same kind of signals that the Monosoft debugger uses on OS X, which means that there's a lot of crossover on the signals, and you end up with the same problem, but it's not solved as easily. So again, the native debugger catches all of the first chance exceptions from the managed code, and you essentially are going to constantly get kind of breakpoints or catches on the native debugger side. You can sort of solve this, and I'll go into that in the next slide, but at 1:15, there's going to be a talk from Jonathan Chambers that goes into details about what we're doing about this in the future with the runtime upgrades. So it will be better in the future, and I'll let him tell you more about that. In the meantime, there's something you can do to help, at least. If you absolutely have to debug native code and managed code at the same time on OS X, you can do this, which is to essentially have Xcode automatically continue after catching this exception. So if you notice in that little screenshot there, we have the process handle sig user1, and on the bottom we tell it to automatically continue after evaluating. So it'll still get the exception, but you're telling Xcode to go ahead and continue anyway. And yeah, you can get to that window just by going to debug breakpoints, create symbolic breakpoint. The only problem is this is not a holistic solution. So because essentially all of the signals are shared, there's gonna be other signals that still get sent to the native debugger that the native debugger might actually need. So you can't turn them off. Otherwise, you'll be ignoring signals that the native debugger might need. So you still get into a situation where the native debugger is going to be catching signals that the mono debugger is sending, even though they might not actually need them, which makes it difficult. Hopefully, again, in the future, that won't be an issue. So, but for now, my advice would be, if you can, debug it on Windows, and if you have to debug it on OS X, do this. Okay, so what if we just want to debug a native, with a native debugger, but we get a managed crash? What does that mean? So if you see here, this is what you'll see in a call stack if you have a managed exception from a native debugger context. So this is the bottom of or the top, I guess, depending on how you look at it, of a call stack. And you'll see those last three lines there. We have, mono.dll, exclamation point, and then the function name. So at the top there we have malloc, and then we've got, a table insert and a mono JIT runtime invoke of a method. So if you see this, you might think, oh, well, we've got a crash in malloc. Obviously it's our last function in the call stack. Maybe we've allocated to a bad memory pointer or buffer overflow or something. So what you need to know is that this is not necessarily a crash in mono. It's not necessarily a crash in malloc. This is very likely a no reference exception in managed code. And it's generally an unhandled exception that has forced the player to exit. So the first thing you need to know is that this is not necessarily what it looks like. If you see something like this, it's just very likely just an unhandled exception. So what do you do about it? So the next thing you need to do is you need to figure out what that code actually is. So the way you can do that, if you're, say, in a native debugger, because the managed frames don't have any useful information, so because we're looking at some kind of generic functions that call managed methods, what you need to do is figure out what those methods are. So you can do that by using a mono utility function called mono_PMIP to identify the managed functions that you have here. And you can do that using the debugger command line, or in Visual Studio, it's the immediate window, is what they call it. And so what that looks like is you input, in the input window, you need to put in the function that you want to run. So in the mono DLL, mono underscore PMIP, and then you want to pass it the address of the call stack frame that you want to process. And then in the output, you should get something that looks like this, which should be a named function on the managed side that you're looking to identify. So you should be able to essentially go through and identify the call stack that you're looking at from a native context. So again, if you're on OS X and you absolutely have to debug some issue and you're having issues with mixed mode debugging, you can always try just using the native debugger, catching somewhere where you need to get some information, and then identify the call stack. Okay, so next up, just to clarify, there's gonna be kind of some we're gonna just jump from tip to tip. So some of these are gonna be really small, useful little things, but these are all essentially in the context of Unity Editor and player debugging. So the next thing up is dumping objects while debugging. So in 2017.1, we actually have these functions that you can call at debug time. So that essentially just dump objects from Unity. So just like we did with the mono function, you can just call these directly from the immediate mode window or the console. And if you need, you can find the definitions for these functions in that file there in the base object utilities. And as you can see, we can use, we have various different parameters that you can pass to get the object that you want. So you can use whatever makes sense in your context. But what this looks like is once you run that function, you should get some human readable text that looks something like this. So we've passed in an object and a flag on what we want to dump, and we get our nice human readable version of all the properties of that object. So this can be useful if you've got objects that you might think are corrupted or have bad data in them, or just have properties that are wrong that you need to figure out. You can use this to help dump that at runtime. Okay, so the next tip I have is speeding up your Visual Studio step times. So one thing you might notice when you're debugging Unity is you have your debugger attached and you're stepping through, and it's super slow. So the reason this is because Visual Studio will automatically evaluate inspected variables by default, all of them. So every time you step, it's going to run all of its inspector evaluation for every variable in scope. So that can be slow. So what you can do is you can uncheck this in the settings by using, you just go to Tools, Options, Debuggings, General, and you uncheck that property or that value there, enable property evaluation and other implicit function calls. So that can help speed up your step times dramatically. You can still inspect your variables manually though. So if you actually have something that you want to inspect, you can add it to the inspect window and evaluate whatever variable you need to. Okay, so next up are going to be some of the specific tools inside the Unity codebase that you guys can use to help solve any issues you have debugging-wise. So the first thing we have up here is the diagnostic switches. So diagnostic switches are runtime configurable debug switches. And what that means is they're essentially variables that you can use to determine what kind of code you want to run at runtime. And this means you can then build in debug code. So if you look here, we have two defines. These are how you essentially define your debug switch. So we take the value type that we want to evaluate for the debug switch, the variable name, and then essentially a string description of what it does. So in practice, That kind of looks like what we have down here. So, if G debug foo checking level, that's one of our debug switches, is greater than 0. Or if another debug switch here, G debug do extra foo checking is on, then we go into this branch and we do some extra debug stuff. So let me give you a little bit of background about why we do it this way. I think probably most of you have written some debug code or something that says something like, if debug enabled, do this, right? And we've got some if-def code that is written to print some stuff or do some sort of debug code. Or you've got some commented code that you uncomment to your printfs that you don't want in the runtime, but you need sometimes for debugging. You've got to comment it out. Well, that stuff doesn't work very well. And it doesn't work very well because commented out code rots. Over time, in a large code base, someone's going to forget about it. That employee's going to leave. Someone's going to not know what that code does eventually. And because it doesn't compile and no one's really looking at it, a year later, it just doesn't work, right? So that's not good. Same with if-defs. If-defs, compile if you're using the flag, which is great. But you have to recompile every time you want to turn it on. And it's something like Unity, where compiles can take a really long time. It's not very efficient, right? And then, lastly, like a couple of different tools. You don't necessarily want your debug code in different places than where you're at. So debug code is most useful in context, which means that if I can write debug code that is within the scope of the problem, that's really nice, right? It's really useful because then anybody can just come to that scope and say, oh, hey, look at this nice debug code we have here. It's easily understandable, and it doesn't get lost, right? If I write some debug utility or something somewhere in the code base, some people may know about it, some people might not know about it, but it's outside of scope and it's hard to find, right? So diagnostic switches are better. And they're better because it's a single centralized system. So there's one place. They are the diagnostic switches. That is it. They're accessible, so you can turn them on from command line. You can turn them on from the editor UI, and you can turn them on even mid-debug session. So that's all essentially free, right? We don't have to recompile. We don't have to go uncomment some code. We don't have to pass in an if-def. It's just there. So it's accessible. And then again, it's always compiled, so it's maintainable. We don't have, commented code that kind of rots over time. So what that looks like in practice. So here's one I took out of the code base. So this is a diagnostic switch to turn on some gizmos for rendering. So at the top there is the definition of the switch. So we pass in the value type that we want. So it's going to be a bool. And then the variable name is going to be gdiag display render bounds. And then I've cut it off, but at the end there is just the description. So it's a string literal with what it does. And then in the actual code where we want to use it, we have a simple if that says if we want to use this diagnostic switch, we're going to add some gizmos. So go ahead and do whatever the debug thing is that we want to do. So again, it's really simple, right? If I was a programmer who came out of the team and I needed to come work on this code, I see it right here. I go, oh, hey, there's a gdiag switch here. I can just turn that on and maybe I can figure out what's going on. So it's really useful. Also, a side note, I actually forgot this on one of my other slides, but you can only, as of today, you can use enums, you can use bools, and you can use uint32s. Those are only types that are supported in these macros. So just a heads up. So what that looks like in the editor is when you build Unity with source code in debug, you actually have this preference diagnostics page in the preferences that pops up. So this is the first way you can turn on diagnostic switches. So, if you, we obviously already have a bunch in the editor, so you can just do a debug build and open this page and see the ones we have available. So yeah, you can use it in the UI. If you mouse over any of these, you'll actually get the description that was mentioned earlier. So if you mouse over any of these, you'll get the pop-up with the text that the programmer wrote in. A couple things to know about this page as well as just diagnostic switches is that they apply to the editor and players. So if you turn them on here in the editor, if you build a player, it's still going to be on in the player. So if you don't want that, make sure to turn it off before you do your player build. Yeah. Okay, so that's the first way. You can come here and turn them on. The second way is through command line. So all of them are exposed via, the prefix diag. So for instance, the example we have here is if we have a variable switch named gdiag some switch I made, the automatically generated command line option is going to be -diag and then dash, word. So you can turn them on that way. And then, for non-Boolean types, so say like you're in 32s, you'll need to pass in the value. So if you, for bools, you can just use the flag. If the flag's on, then it's true. If it's not, it's false. And then for other types, you have to pass the value in that you want on the command line. And then the last way is in the debugger. So all diagnostic switches that get generated will have a set value function that gets generated alongside of it, or for the class. So in the debugger, again, using the immediate mode or console window, you can just call the set value function on the switch itself, and set the value to whatever you like. So this can be done at runtime, which is great because it's immediately accessible. If you already have a debug session and you already have the problem caught, you don't want to let that go and then have to turn a switch on and then come back and try to reproduce it again. So you can just go right to the immediate window, turn the flag on. The only thing you need to know is that, my note here is that some switches are evaluated at startup. So there are going to be switches that just might not work that well at runtime. So make sure that whatever switch you're using is kind of applicable to what you're trying to do at runtime. Because you might have to actually go back and turn it on and reinitialize the engine. Just depends on which one you're using. Okay. So that covers diagnostic switches. And then next up, we're going to talk about leak detection. So Scott talked a little bit about this. But it's a pretty simple system within the code base. So if you want to check out kind of the definitions for stuff, you can go to memoryprofiler.h. But essentially, the two definitions that you're looking for are the record allocation sites and enable stacks on all allocations, which is also the flag you can use to get the call stack allocations in the profiler. But this one's really simple. Once you turn those on, you can essentially run your test case. You drop a breakpoint in this function here, memory profiler report allocated memory. And what you can get is on that leaks variable there, you can inspect that to see the list of all of the live allocations still in the list. So you can also see that it actually gets printed. So in debug builds, you'll actually get a log in the console with those leaks, with these on. So you don't even necessarily have to debug this. You can just turn this on and read the logs. One thing you should note about this is that this is all wrapped up in the memory system, our memory allocators. So with anything memory related in Unity, if you're not kind of allocating stuff into our allocators or into our memory framework, then this stuff isn't going to be very useful. So if you're building a lot of tooling or new runtime stuff that's allocating outside of our memory allocators, then sorry, you won't really. This won't be very useful. Which goes to the same for the debug allocator. So again, same thing. Debug allocators are really nice if you are allocating stuff within our memory system. So what debug allocators allow us to do is they do stuff like buffer overrun detection. They detect freed memory access. If you want to check them out, you can go to this location here. That's the file that you'll find debug allocators in. When you turn debug allocators on, they essentially replace the regular non-debug version of the allocator. And what they do is they essentially allocate extra space in the heap, or per allocation, to determine when there's overruns. So we can actually tell, like, oh, hey, we've crossed over our boundary. So we know that, and we can catch it. It's available on OS X 64-bit and Windows 64-bit configurations only. So debug allocators take a hell of a lot more memory than regular allocators. So they're pretty much only available on 64-bit platforms, aka Mac and Windows 64-bit. But it does work for the players and the editors. So you can turn debug allocators on with a diagnostic switch, which we just covered, so you should know how to do that. But yeah, you can do it either, that's the switch there, the gdiag force debug allocator. And you can do that also with the command line -debug allocator. Debug allocators, again, work for all memory labels within our default allocators. So if it's within the memory scope of Unity memory, like Unity containers, like Unity vector, Unity hash set, etc., or if you've registered that memory in our memory labels. But the way they work, essentially, it's really simple. When the debug allocator detects one of the two conditions that we talked about, you'll just get an assert message with data in it. So you can essentially just have it on and then be debugging, and it'll catch it, and then you'll have some context to what's going on. OK, so that covers debug allocators. So last up, we're going to talk about debugging runtime tests. So out of curiosity, just because I want to know, how many people in this room have actually run, non-Unity employees, by the way, don't raise your hand, have actually run a Unity test from the source code? Like a runtime to any of our tests, runtime test, performance test, anything? One guy. OK, that's what I thought. So this might not be that useful because you guys aren't running tests anyway, so debugging them isn't that useful. But I'll talk about it anyway since I have the slides. So if you do have a failing runtime test, there's a couple things you want to think about before you start trying to debug it. The first one is, does it fail using the unified test runner, or does it fail standalone? So when you run tests in Unity, I don't have any slides about how to run tests in Unity, but maybe I'll talk about it really quick just so you guys have some context. So when you run a test in Unity, you can do it two ways. You can do it from command line. So you can say, I can't remember the exact command line option, but it's essentially, you do it through the build system. You say Perl, build PL, run test, blah, blah, blah. You pass the test name in you want to run. Or you can tell our test system to run a suite of tests. So you can say, hey, run all of the runtime tests, or run all of our performance tests. Whenever you tell the test runner to run a suite or any kind of grouping of tests, it gets run through the unified test runner. And the unified test runner is essentially going to run a bunch of different tests on the same Unity project. So what that means is, it's going to generate a Unity project. It's going to shove in some code. It's going to shove in some assets. It's going to shove in the test. It's going to run the test. Yay, it succeeds. It'll clean up the project, and then it'll shove in the next test. But what that means is the unified test runner can run faster because we don't have to generate brand new projects every time we want to run a test. We can just kind of shove in the content. The bad news about that is that if we have a failure, it's a little wonky about whether the unified test runner failed or whether the test itself failed, or maybe a previous test broke something so badly that the next test failed even though the one that broke it succeeded. So whenever you have a failing test, the first thing you need to do is separate it out and determine whether it's actually the test. So that means you have to run it individually. And you can, again, do that either via command line. You can run the test by name on command line, or you can do it in MonoDevelop. You can tell it to run the specific test in the testing suite. So now that that's covered, once you determine whether it's the unified test runner or just the individual test, assuming it's the individual test, how do we actually debug that? So you run the test in Visual Studio, want to develop, or via command line. It doesn't matter. And then what you need to do is you want to start Unity and open the temporary project generated by the test runner. So when a test is run, it's going to generate the project. It's going to open in Unity. It's going to run it. It's going to fail in this case. And then what that means is that the test project itself will still be in the recently open projects list. So you can actually just open up the launcher and it'll be right there. You'll see like a long string of where it was generated. The actual test projects are generated into your platform's temporary folder. So like on Mac OS X, it's going to be like var / whatever, a bunch of garbage characters. And then you'll find the Unity project somewhere deep in there. The easiest way really though is just open launcher and it'll be in the recently viewed list. And then once you have the actual test opened in Unity, so once the test is run, it'll create the Unity project, it'll push that project into the platform's temporary folder, and then it won't destroy it. So once you run a test, that project will still be there. So you can then just open it up. You'll have the test in Unity with all the assets and the scripts for that test, and then it's actually as simple as just debugging any Unity project. So it's the same. You're going to just open them on the develop, you attach, run the test, and there you go. You're debugging the test. So it's pretty simple. One side note is if you are running tests from command line, so if you wanted to debug the test and you wanted to start it from command line, you need to set this environment variable here, Unity give chance to attach debugger. Otherwise, it'll just run the test and it'll be done before you know it. This allows two pop-up windows, one to attach a native debugger and one to fetch a managed debugger. And yeah, that's about that. So that's my talk. Do we have any questions? No? OK, I didn't think so. All right, well, thank you.